So there is an equation that gives us the relationship between the current through the diode versus the voltage across the diode versus current through the diode, and it is an exponential relationship, as you can see on the screen here. So you should be able to see two screens. One is the experiment write-up, and the other one is the proto board. Right now, I recommend that you make the the experiment write-up your main screen. Um, so you have current through the diode over here, which is ID. It is equal to the saturation current, the current that flows in the through the diode when you are in the reverse bias region of the order of nanoamps, so very small. And inside the parentheses, we have the exponential function Vd, which is the diode voltage across the diode, divided by n, which is a value that is typically between 1 and 2 that you can change. Vt is the thermal voltage of value 0.0259 volts minus 1. Minus 1 is not in the exponent, it is by itself. So that's a relationship, that's an equation that dictates the current voltage characteristic of the diode. So we are able to sketch this in MATLAB, for example. And we can also do an experiment, and we'll be doing that using the 1N4148 small signal diode, and we'll use the analog discovery to measure the voltages. Then we'll use a current sensing resistor to measure the current through the diode, and we'll have a CSV file with all that data. We will take all that data through that CSV file into MATLAB and do our comparison between experimental and theoretical equation. So that's going to be our task for today. Um, so what I want to do is quickly talk about the different simulations and the circuit building exercises that you have in part A and part B of experiment 8. So the ones that you see highlighted in yellow, they are all going to be simulations. So that's your capture PSPI simulations. So I'm going to let you guys work on that. So this first one is to sketch the IV characteristic of a resistor. We all know that that should be a linear one. So you should see a linear equation like such. Figure A-5 shows us what to expect. Um, and then in figure A-6, you are still doing the IV characteristic using the simulation. And then when we come to figure A-7, that's when you have the IV curve of the real diode. So what I have in the other picture is essentially uh, the I have wired the circuit that is shown in figure A-7. So what I'm going to do is quickly talk about the connections over here, and then I'll talk about how I made them in the circuit board. This is going to be very straightforward. You guys should like be very familiar with this. Uh, so this should go quickly. On this particular point, we have WaveGen. So I'm going to be using a yellow wire from Analog Discovery to make that connection, and I'm going to set up my WaveGen based on what is given in the experiment write-up, which is essentially a triangle wave of amplitude 5 and frequency 1 kilohertz. So I'm going to set it up when I start WaveGen. Um, then I know WaveGen can go between plus and minus 5. So the highest voltage on that triangle, I can set that to plus 5, and the lowest can be minus 5. But if I want to explore a little bit of a bigger range in terms of voltage, then I can do that by using my negative power supply. So what I'm going to do is use the white wire from Analog Discovery, which is the negative power supply, and I can set that to, for example, negative 4 volts. So because this can go from plus 5 to negative 5, with a reference of negative 4, essentially I'm going to be uh, exploring voltages that are from what 1 to negative 9. So a very large, uh, sorry, if this is plus 5 and this is negative 4, then it is plus 9 with respect to ground. You see, if this is plus 5 and this is negative 4, that point is at a voltage positive 9 if I thought of this as my reference. So I'm going to explore a bigger voltage range if I am able to connect a negative power supply. And all of this is explained in the paragraph over here in the write-up. Then I have two scope channels. One is across the diode, the other one is across the resistor. The one across the diode is channel 1. I have connected the orange stripe wires for the diode. The diode itself has polarity like we discussed. So if you look at the diode, and if you are curious, I would recommend that you look at the data sheet for 1 and 4148. It will essentially be a two terminal element that looks like that. I don't know if you guys can see it very well, but that it is right there. um, and it has a orangish tinge to it. In very small letters, there is 1N4148 written on it. But what I can clearly see is that there is a black ring on the bottom side of this diode, and that is the negative terminal or the cathode, which is why I've connected it away from my resistor. Because based on the circuit, the anode, the positive terminal, is connected to the uh, end of the resistor R1, and the negative terminal is connected to the negative power supply. So I've made that connection. The resistor I'm using is brown, black, red. So that's your 1 kilo ohm resistor. And across that, I've connected the channel 2. So 2 plus, the blue wire is connected to yellow, is connected to R1 over here. And blue stripe or 2 minus is connected to orange wire is connected to these two ends of resistor and diode. So all of that is over here, that right, that point. Not too many things, and very simple circuit in comparison to the others that you have seen before. um, Voltage source, one scope across diode, the other voltage scope across the resistor, and a negative power supply over there. So now what I'll do is I'm going to look at, for example, I can switch off my hover cam and bring in the waveforms. So in the experiment, do I need wavegen? Absolutely yes. Do I need scope? Yes. So I need scope. I'm going to turn that on. I need wavegen, yes, and I need supplies, yes. So let me work on the supplies first. I don't need the positive one, but I definitely need the negative voltage supply, and I'm going to set it to -4. Let's see, -4 right there, and it is ready to be turned on. Next, I'll go to wavegen, set it to a triangle wave. Frequency is 1 kilohertz and amplitude of 5 volts. Done. And I'm going to go to scope, and let us try to estimate what the time base needs to be set to. Even before I turn on scope, I want to go through this exercise of looking at how to set the time base or the x-axis with the information that I have. Instead of doing it in a trial and error fashion, how can I do it without that? So if you think about the frequency of the voltage source, we set it to 1 kilohertz, which means that the time period is going to be 1 millisecond. And if you are interested in taking a look at two time periods, then that is a 2 millisecond time window. And waveforms divides things up into 10 divisions. So if you take a 2 millisecond time window and divide it into 10 divisions, so that is 0.2 millisecond per division, or 200 microseconds per division. So I will directly set the time base to 200 microseconds per division. I will keep the position to be 0. Then my channel 1 and channel 2, I will set them to a high value because I'm exploring a lot of voltage here. So 2 volts per division each for channel 1 and channel 2. And now let us switch on all the things. So I'm going to turn on supplies and wave gen and scope. So right away I start getting my results. To make it a little bit better, perhaps no, 4 is too much. 3 is probably good. All right. So channel 2 is good. Channel 1, I can maybe zoom in a bit more. So I'll make it 1 volt per division over here. So channel 1 is essentially your voltage across the diode. As you can see, the voltage increases as the source is increasing. And then it limits to 0.7 volts, which it is doing over here. And then on the negative cycle, it will simply follow the source. And the blue line is the voltage across the resistor. So that is essentially the source voltage minus the voltage across the diode to get that. So in our discussion, we were using sinusoidal waveforms. It's exactly the same relationships, but triangle waveform over here. So that's your voltage across diode and voltage across resistor. I was interested in the current through the diode. So how can I do this in waveforms? Well, I can do that in waveforms if I have the current through the resistor as one of the measurements. So I can actually set up a math channel. So I'm going to select math, custom math, and I'm going to change this equation to C2 divided by 1000. C2 because voltage across the resistor is measured on second channel, and 1000 because the value of the resistor is 1000. And I'm going to also change the units to amps, and I'm going to say okay. And when I do that, I see some new line very close to 0. So just to see what it is, I'm going to turn off channel 1 and channel 2, and I'm going to try to zoom in on math 1 by setting the range to perhaps 2 milliamps per division. So when I set it to 2 milliamps per division, I can now see the current through the resistor, which is also the current through the diode. Um, and now that I have the current, I can bring back my channel 1 and channel 2. So all of this, as you can see, when I turned on channel 2, it actually went right on top of the math channel, because math channel, all that is channel 2 divided by 1000. Our channel 2 is 2 volts per division. Math channel is C2 divided by 2 milliamps per division. So because there is a factor of 1000 at both those places, they cancel each other out and they are landing on top of each other that way. Okay, so now I have voltage across diode, current through the diode. I should be able to sketch the current voltage relationship for the diode. And before I actually take this data into MATLAB, I can actually do a quick check in waveforms itself. So there is a view option in waveforms where you can add XY, meaning one of the channels set on the x-axis versus one of the channels being on the y-axis. So when I select add XY and maybe zoom over here, increase the width to maybe 3, maybe even 4 here. And on the x-axis, I have it default as channel 1. Yes, I want that to be channel 1 because x-axis is voltage across the diode, and that's what I want it to be. Y-axis is not channel 2. I actually want that to be the current through the diode, so M1. And now maybe I can zoom in a little bit. So I can zoom in on the X. So instead of doing the range of 1 volt per division, maybe if I do 200, millivolts per division, I can see the exponential rise of that current when we are going to be very close to that 0.7 volts value. So this is 0.6 right here, this is 0.8, around that 0.7 mark it shoots up. um, so I know that this is a good data set and I'm ready to export it to MATLAB. And the way I do that is by doing a file, do an export, and I'm going to take a look at the data. I have 4 columns over here, one for time, channel 1, channel 2, and math. Time, yes, I need that. Well, I don't really need that for IV characteristic, but just for the sake of having it, let's have it. Channel 1 is for sure necessary because that's the voltage across the diode. Channel 2 is sort of unnecessary now because we already have the current through the diode in the 4th column, but let's just have it here, channel 2. And then the last column is of course necessary because that's the current through the diode. So we really need the 2nd and the 4th column to go to MATLAB, to be imported to MATLAB. But I'll save the entire file. So I'm going to say save. It's going to save. Where do you want to save and in what format? I'm going to save it as a CSV file, and I'm going to call that, say for example, uh, data 2 for example, and I will save it and done. So my waveforms part for this part of the experiment is done. Now I'm going to try to take a look at what I can do in MATLAB. So give me a moment here while I set up MATLAB and bring that over here. I hope you guys are able to see the window. In fact, give me a moment. I'm going to make the view better for myself. Let's see, data, and all right. So I've essentially changed. Um, well, for you it might not be a big change, but I hope you guys are able to see my MATLAB window. Maybe it is convenient to see, maybe it is not. I don't know how your experience is with the dark background. So if you guys can let me know if it is okay or it's good. Okay, all right. So when you start MATLAB, and if you are a first time user of MATLAB, this is going to be a useful discussion now. What I have is I have one window over here all the way to the left, which is called current folder. So that is essentially showing me the contents or all the files and subdirectories in my current folder. Right now I'm working in the MATLAB directory, and there is also a window called command window. So if I wanted to type in some commands, for example, clear, CLC, and some simple commands, a equals 5 for example, so I can do all of that in the command window. And notice what happened when I entered a equals 5. It not only echoed it back to me because I said no semicolon earlier, so if you use a semicolon then it will not echo it back to you. But more importantly, when I typed in that command, you see what the change was in the workspace. A is set to 5. So basically, workspace is a very, very useful window that allows you to keep track of all your working variables and matrices. And then command history is sort of self-explanatory. It is going to keep track of all the commands that you typed. The last 4, we just typed it just now. Um, and apart from all that, we have a Matlab editor. So if you want a few commands, like maybe 2 or 3 lines, then command window is going to be okay. However, if you have 100 lines of code, then you don't want to type all of that in the command window. Instead, you want to maybe write it up as a MATLAB script and then run it all at once. And you do that using the Matlab Editor. So, and they have an extension of .m. So that's what we are going to do today. We are going to write a MATLAB script that takes in the experimental data, fits exponential theoretical equation to that, and then plots both of them on top of each other so that we can see how well it compares. So let's see. What I'm going to do to start off with is import that data. So let's see. How can I import the data? I'm going to go to Home, and I'm going to select Import Data. And please pay attention here, because these steps you guys are doing it by yourself. I'm just giving you the CSV file. So when I do the import data option there, under Home, I can go select my CSV file now. I just saved data. Oh, not project 3. Experiment 8, data 2 is right here. So I do that. And once I click data 2 and I start that, it is going to uh, give me this particular window. So this is your open import data wizard, and it is highlighting a few columns, 4 columns of my CSV file that I may want to import. And the default option over here is column vectors. So it is giving me an option to import it in the form of a vector each, or maybe a matrix, or maybe a cell. Well, cell is not appropriate for this, but column vectors or numeric matrix is okay. So as a one matrix or individual columns, I can uh, take up any option. Let me take numeric matrix, for example. The data is already highlighted. In the first column I have time, second column I have voltage across diode, third column I have voltage across resistor, and in the last column I have current through the diode. So I'm going to it's already highlighted, so I'll just say import selection, and I'm going to click on the check mark so that it does it. And I'm going to minimize this, and the moment I do that, I hope you see now that there is, in the workspace, there is data 2, and the value of that is 8. So sorry, the size of that is 8192 rows and 4 columns, and the format is double. Note that I'm going to write this command as a comment here. If data 2 is in table format, then use you are going to have to type in this command where you say data 2 equals table 2 array of data 2. So you essentially take whatever you have in the table format, use the command table to array to convert it into double format, and then give it back to the same variable data 2, and then we can write the code. So I need to do that only when the data is in the table format. So keep track of that in your workspace. But right now we have imported it as a numeric matrix, so it got the data in the double format directly, so we are good. So let me do this. What was the time? Time was the first column. So how do I say the first column? I say data to all the rows, first column. That's going to be my time. Then I have let's see, what is going to be the voltage. So VD, voltage across the diode, is data 2 all rows, second column. What is the current through the diode? ID, data 2 all rows, fourth column. Note that I could have also done ID equals data 3 divided by 1000. I could have done that as well. The percentage sign is the comment, so that doesn't get executed. Only the statements do. Let's see. So I've got time, I've got VD, I've got ID. I just need to plot it. So let's do plot. What do you want on the x-axis? VD. What do you want on the y-axis? ID. Do you have any color preference? Maybe just a black dot. All right, so let's say I run this. Running is F5. So if I press F5, it is going to ask me to save it. I can say some maybe EI exp8 underscore Matlab, and it is already running. Yes, it is busy, and then it gives me that particular plot. So K over here is the black identifier, and the dot is it put dots wherever it had the data, and you are able to see what exactly the same thing that we saw in waveforms earlier. So I can do a few more things here. Let's see if I can maybe put this here and put this here. Every time I run this, I want things to kind of uh, restart. So what I'll do is at the beginning of my code I'll put close all, which means that it is going to, the first thing that it is going to do is it is going to kill this figure window and then regenerate it. So that way I don't keep overwriting on the same plot. Next, do you want a grid? Yes, I do want a grid on this plot. And do you want an X label? Yes, I do want an X label. What is it? It is going to be voltage across diode, and the units are volts. Now again we can type in the Y label next, parentheses, quotes, by label I can have current through the diode, and the units are going to be amps. Actually, you know what, instead of doing it in amps, let's do milliamps. Milliamps. However, because I'm plotting it in the form of milliamps, I'm going to make this plot ID, and I'm going to multiply that by 1000. So notice over here what I did. So I ran it again, and when it comes back up this time, it is going to show me the current through the diode, and as you can see, I adjusted the units to be milliamps, so it's just showing me 1 2 3 4 and so on, because I adjusted the Y data by multiplying it by 1000. On the X, I have the voltage across the diode in volts and the current through the diode in the Y axis. It also put a grid over here. All right, let's continue. Actually, because I'm going to use this in the form of a curve fitting exercise, I will remove that, and I will leave this in the form of amps. And let's see, now I can start working on the curve fitting. So for that, I'm going to take a look at the experiment write-up. So let's see, EI page, links experiment, experiment 8, da, 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 and all of this information is there provided in the experiment. The code is given, but I'm writing it from scratch. So I did all the plots. Hold on is useful. I'm going to do that next, but I'm also interested in doing these things. So the diode equation is what I'm going to copy from here, and I'm going to essentially paste it over here. So I'll make this window bigger now. Okay. Um, so IS, the saturation current, is defined as 0.8 times e to the negative 14. I can play with that parameter so that it fits very well. N is set to 2. VD is going from 0 to 5 volts in steps of 0.01. So that's my x-axis for this equation. And this is essentially the same equation that we talked about at the beginning of this this video here, which is the exponential relationship. Has the saturation current, it has the voltage across the diode, it has the thermal voltage, it has the factor n, which is between 1 and 2, and so on. Now, because we have two plots, when I run this, one thing is going to plot over the other. You can, sorry, the first thing is going to get printed, then it is going, when it, before it plots the second thing, it's actually going to get rid of the first thing. I don't want that. I want that to be preserved. So I'm going to include the command hold on here, and let's see how it prints. This is with a thicker line width. 3 is the line width, and it is going to plot in red in this case. F5 generates a new plot, and let's see how that looks like. So it looks like things have gone off scale, meaning my black line is very, very small and my red line has become so big. So what I'm going to have to do is I'm going to have to limit things in the X and Y direction. So if I zoom in on this part using the zoom in tool, we might be able to see that things don't, well, I'm not able to see it here very clearly, but we don't really need all the x-axis. So I can use the axis command to limit the plot x and y limits. So x, I can say, let's see what is the video. So 0 5, so this is what is given to us. Let's see if this works. If not, we can adjust it. All right, let's see if that does it. I ran the program again and it generated that for me. So this is looking good. I can make it a little bit tighter. uh, so what are we going to do from here though? Well, our experimental data is the black line. The equation, theoretical equation, is the red line. My goal is going to be to change is and n, these two parameters, so that they closely match. So I'm going to adjust that. In fact, if I just want to change one of them, I can just change one of them and see if I can get them to line up. And then I will add a title. I will also add a legend because we have black and red here. So let's do all of that. Let's see. First things first, I will change value of n to 1. See how that works out for me. Next, I'm going to add a legend. The first thing that we plotted was the experimental data. And the second thing that we plotted was the theoretical equation. And we can also add a title to this plot. And the title will be current voltage diode 1N4148. Okay, I think we are good. I think that's all we said. Let's see if this works out. Run it again. New plot generated. Where is it? Come on. And it now looks like this. So we got the title, we got the legend. However, so we are wasting all of the space. So I'm going to play with my axis command and limit this to perhaps maybe even just like right here. Like 0.8 would be okay, 0.85 would be okay. So let's do that on the x-axis. Instead of going all the way to 5, let's just make it 1. Run it, see how that looks like. All right, so things are getting better. I guess this is where I'll stop. I think I've given you pretty much all the things that you would need to kind of align them very well. As you can see, they are getting closer to each other. You can work on getting them a little bit more closer. and that's what you would use in your reports. Note that there are some very cool things you can do with the plots, and I would like to show you a couple of them. If you go into file, for in the figure window, if you go into file and you select export setup, it gives you a setup that you can apply to your figure window. So you can change the size, you can change the fonts, you can change the line, so you can change all of that. However, what I like to do is I like to use an existing style. So I load a presentation style which I like. I load it, then I apply it, and the moment I apply it, the figure window, now you see, for me that's a existing setting, style setting, that I prefer to use. So I use this a lot, even for the the histograms I generate, the bar graphs I generate for your quiz scores, the distributions. I use the same setting for that. um, and then you can do uh, edit, copy figure from here, and then paste it into your Word document, for example. um, so I hope this was helpful. I am going to see if you guys have any questions right now. Kendy says, for project 3 simulations, which 555 timer part are we supposed to use? Please use 555D. So it should be in the eval library or evaluations library. I have seen that some of the students were using the correct component, however it was from a different library, which caused it to throw an error that we were using too many nodes. So 555D from the eval should be okay. All right, coming back to the MATLAB thing, I hope you guys have you are okay with the MATLAB part. I don't want to get ahead in terms of section 1 and section 2 synchronization, so I'm going to stop over here, and I will we will pick things up when we meet again on Monday. So let me actually stop the video recording, and